Nobody told you the moon had a secret side. Not NASA, not your textbooks, not the scientists who spent decades pointing telescopes at its glowing face. They studied the side we could see, mapped every crater, named every ridge, and called it understood. But the other half, the side permanently turned away from Earth, the side that never faces us, the side wrapped in perpetual cosmic silence, that side they left alone. And then an AI started looking. And what it found did not just surprise the scientists. It rewrote 4 billion years of planetary history in a single scan. There's a side of the moon that no human eye has ever seen from Earth. Not once. Not in all of recorded history. Not from any mountain peak. Not through any telescope. Not with any naked eye gazing upward on a clear night. The moon is tidally locked to our planet, meaning one face always greets us while the other face permanently hides. Turned away into the darkness of space, silent, cold, and for most of human civilization, completely unknown. Scientists called it the far side. Some called it the dark side. But neither name really captures what it is. What it actually is the most mysterious terrain in the inner solar system. And for decades, the world's greatest space agencies were too afraid, or perhaps too underfunded, to go and truly look. That changed in 2024, when China did something no country had ever done in the history of human civilization. The Chang'e 6 mission landed on the far side of the moon, drilled into its ancient soil, and brought back 935.3 grams of lunar material from the South Pole Aitken Basin, the oldest and largest impact crater not just on the moon, but in the entire known solar system. Think about that for a moment. The largest crater in the solar system, a wound in the moon's surface spanning approximately 1,250 miles across, wide enough to swallow the entire continental United States, and scientists had never held a single physical sample from it, until now. But here is where this story stops being about geology. Here is where the real narrative begins. Because once those samples returned to Earth, researchers faced a problem no amount of human analysis could solve quickly enough. The data was too dense. The patterns were too subtle. The relationships between chemical signatures, mineral compositions, magnetic readings, and isotope ratios were too interconnected for traditional scientific methods to unpack within any reasonable time frame. And so, the scientists did something that would have seemed like science fiction just a decade ago. They handed the problem to artificial intelligence. And this is where Grok enters the picture. By early 2026, Grok, the AI system developed by XAI, now operating as SpaceXAI under Elon Musk's merged empire of SpaceX and artificial intelligence, had evolved into something that most people on the outside world still had not fully grasped. The public saw a chatbot. They saw a tool that posted on X, answered questions with a rebellious wit, and competed with ChatGPT for monthly active users. But what was happening inside the walls of its underlying architecture was something far more significant. By March 2026, Grok's monthly active users had surpassed 117 million according to SpaceX's own IPO filing. But the user count was never the real story. What most people are not seeing is the timeline of how this happened. In early 2026, Grok's 420 beta model had introduced a multi-agent architecture, a system where 4 specialized intelligence agents named Grok, Harper, Benjamin, and Lucas operated in parallel, cross-checking each other's outputs, catching errors before they propagated, and pushing the hallucination rate down to an industry-leading 83% accuracy threshold, a 65% reduction in errors compared to just months earlier. That is not an incremental improvement. That is the difference between a tool that makes interesting guesses and a system that produces findings rigorous enough to publish in peer-reviewed scientific journals. And when that system was pointed at the data coming from the far side of the moon, the results shook the planetary science community to its foundation. The first thing AI analysis of the Chang'e 6 samples revealed was something that upended a model scientists had held for decades. For a long time, geologists understood that the moon's near side and far side were dramatically different. The near side, the face you see every night, is relatively flat, dark, and covered in volcanic plains called Maria. The far side is rugged, heavily cratered, and almost entirely devoid of those volcanic plains. Scientists knew the two sides were different. What they did not know was exactly why. The traditional explanation was satisfying on the surface, but vague in its mechanics. Now, with AI sifting through thousands of data points from the returned samples, the answer came into sharp, unprecedented focus. The difference between the two sides of the moon traces back to a single catastrophic event that happened approximately 4.25 billion years ago. One impact, one collision of almost incomprehensible violence, and from that single moment, the entire geological destiny of the moon was split in two directions forever. But here's where it gets worse, or more accurately, here's where it gets stranger, deeper, and far more consequential than anyone initially anticipated. And what they found was that the far side soil is fundamentally, structurally different from anything brought back by the Apollo missions decades ago. The particles are more irregular in shape, more angular, more interlocked. The mean three-dimensional sphericity of these particles measured at 0.74, a number that sounds technical but carries enormous practical weight, because what it means is that the far-side regolith has a significantly higher shear strength than near-side material. It grips itself. It holds together under pressure in ways that the lunar soil astronauts walked on during Apollo simply does not. An internal friction angle of 47.96 degrees. A cohesion measurement that engineers have never seen in any lunar sample before. Read that again. The far side does not just look different from the near side. It behaves differently at the particle level, at the molecular level, at the level of physics that would determine whether a structure built there would stand or collapse. The thermal asymmetry between the two lunar hemispheres is not a superficial surface feature. It goes deep. It goes all the way down into the mantle, the region of molten or semi-molten rock that lies beneath the moon's thin crust. And the reason it matters is not academic. A cooler mantle means less volcanic resurfacing over geological time. Less resurfacing means older surface features are preserved. Older preserved features mean the far side is, in a very real sense, a time capsule. A geological archive of the early solar system that the near side's volcanic activity has largely erased. The far side of the moon is not just different terrain, it is a different era. Standing on the far side would be, in some ways, like walking on the surface of a world that existed before most of the geological processes we associate with planetary evolution had fully begun. Scientists have found evidence of ancient volcanic activity there that doesn't match the models. A magnetic field that rebounded approximately 2.8 billion years ago, the first paleomagnetic data ever collected from the far side, suggesting that the moon's internal dynamo did not decay gradually as previously assumed, but fluctuated, pulsed, and possibly revived in ways that current models cannot fully explain. Read that again. The moon had a magnetic field. It weakened, and then it came back. In a region of the moon that nobody had physically sampled until 2024, detected by AI systems analyzing data at a resolution and speed no human team could achieve alone. And buried beneath the South Pole Aitken Basin, beneath the water ice, beneath the ancient regolith, beneath the mantle-derived rocks that astronauts may soon literally walk across, is something that was discovered in 2019 and has never been fully explained. An anomalously dense mass of metallic material. A buried structure covering an area 5 times larger than the Big Island of Hawaii. Scientists proposed that it might be the remnant core of the asteroid that created the basin 4.25 billion years ago. A metallic impactor so large that when it struck the moon, it didn't fully vaporize. Instead, parts of it sank into the lunar interior and have been sitting there ever since, untouched, preserved, a relic of the early solar system embedded in the moon's body like a shard of cosmic history. This is where the AI analysis becomes not just scientifically significant, but strategically explosive. Because if that metallic mass is what scientists believe it to be, the dense iron and nickel core of an ancient protoplanet, then the South Pole Aitken Basin is not just a source of water ice and geological data. It is potentially sitting above one of the largest deposits of metal ever identified in the inner solar system. Metal that, if it could ever be accessed, would represent a resource of almost incalculable value. In a future where space-based manufacturing is not speculative but operational, where companies like SpaceX AI are already drawing blueprints for lunar factories, where Elon Musk is describing mass driver catapults launching satellites from the moon's surface. In that future, a buried reservoir of metallic ore beneath the very basin that every space agency is racing toward is not background detail. It is the central prize. The real story is not about a single AI scan. The real story is about what happens when the most powerful AI systems on Earth, systems processing data at a scale and resolution that no previous generation of scientists could have imagined, begin examining the one place in the inner solar system that has been hiding the most information. And what they find begins to rewrite not just our understanding of how the moon formed, but our strategic calculus about what the moon is worth and who is going to control it. Consider what has already shifted. In the span of roughly 2 years, from the moment Chang'e 6 returned its samples in June 2024 to the latest published research in June 2026, the scientific picture of the lunar far side has transformed almost beyond recognition. The formation model of the South Pole Aitken Basin has been overturned. The thermal structure of the lunar interior has been revised. The magnetic history of the moon has been extended and complicated. The soil mechanics of the far side have been found to be categorically different from anything in the Apollo dataset. The presence of mantle-derived rocks at the surface has been confirmed, rocks that future Artemis. Astronauts will be able to physically pick up and examine materials from deep inside the moon that the violence of that ancient impact scattered onto the surface 4 billion years ago. And a buried metallic anomaly the size of 5 Hawaiis sits beneath all of it, silently waiting. Each one of these discoveries, on its own, would have been the headline science story of any previous decade. Together, arriving within months of each other, processed and cross-referenced by AI systems running at a speed and analytical depth that traditional science could never have matched. Together, they represent something that doesn't have a clean name yet. Not just a series of findings, a compression of understanding, a sudden AI-accelerated collapse of ignorance about one of the most consequential pieces of real estate in the solar system. And the timing is not coincidental. The AI capability curve and the lunar exploration curve have reached an inflection point simultaneously. Grok 4.5, released on July 8, 2026, represents a 1.5 trillion parameter model trained on real-world engineering workflows and scientific data at a resolution that previous generations of AI couldn't approach. While a 6 trillion parameter model, Grok 5, is reportedly still in training on the Colossus 2 supercomputer cluster. XAI is spending approximately $1 billion per month on infrastructure alone. NASA's Artemis mission is targeting the same basin that AI has just finished recharacterizing. China's next lunar missions are in active preparation. And Elon Musk is drawing blueprints for a computing facility on the moon, while his AI subsidiary processes the geological data that determines whether that facility can actually be built. 3 civilizations, 3 competing visions, 1 basin, and an AI that has already seen more of it than any human explorer ever has. What does this mean for the next decade? That question is the one that nobody in mainstream coverage is asking loudly enough. The geopolitical competition for the moon is no longer abstract. It is no longer a distant future scenario reserved for speculative fiction. The Artemis Accords, the framework the United States has used to build a coalition of partner nations around a shared lunar governance vision, have been signed by dozens of countries. China's International Lunar Research Station framework has attracted its own coalition. These are not cooperative projects. Oh, they are competing jurisdiction claims dressed in the language of science and exploration. And the basin they are both converging on is the same one that AI analysis has just revealed to be far more valuable, far more complex, and far more strategically significant than anyone had publicly acknowledged. There is a concept in military strategy called a key terrain objective, a piece of geography whose control determines the outcome of everything else. In the next century of space development, the South Pole Aitken Basin is that terrain. The water ice makes it a fuel depot for deep space. The mantle rocks make it a geological laboratory for understanding planetary formation. The metallic anomaly buried beneath it makes it a potential resource site of staggering economic scale. The far side radio silence, shielded from Earth's electromagnetic noise by the moon's own body, makes it a perfect location for observatories, for sensitive scientific instruments, for computing infrastructure that requires an electromagnetically clean environment. And the soil, as AI has now confirmed, is stronger and more structurally sound than anything Apollo ever touched. Every advantage that makes the far side uniquely valuable was invisible until the AI looked. Every characteristic that makes the South Pole Aitken Basin uniquely important was either misunderstood or entirely unknown until the samples came back and the algorithms ran. This is not the story of a geological survey. This is the story of a strategic asset being fully characterized at precisely the moment when multiple great powers are mobilizing to claim it. And here is the question that nobody is answering publicly, because answering it requires acknowledging things that governments and corporations prefer to discuss in private. What happens when the AI working for one of those competitors has already seen more of the terrain than the others? What happens when the system processing the data? The far side of the moon spent 4 billion years in silence. It kept its secrets through every telescope ever pointed at the sky. It kept them through the Apollo era, through the Cold War space race, through every orbital survey and remote sensing campaign that the 20th century could deploy. It held onto its geological history, its thermal asymmetry, its buried metallic anomaly, its stronger soil, its ancient magnetic pulses, its evidence of impacts that reshaped the entire evolution of Earth's nearest neighbor. It held all of that, undisturbed, for longer than complex life has existed on this planet. And then an AI looked, and in the time it takes a human scientist to write a single paper, the machine had mapped what 4 billion years had hidden. What is about to happen on a world that has no atmosphere, no inhabitants, no flag, and no precedent? Because the race has already started. The data is already in, the plans are already drawn. And on the far side of the moon, 4 billion years of silence is about to end in a very loud way. Something is coming. And the AI already knows what it looks like. Think about what that means. Every blueprint, every simulation, every engineering calculation that space agencies around the world have been running for future lunar bases has been based on near-side soil data, Apollo data. Data that, it now turns out, does not apply to the far side in any reliable way. The foundation that future lunar architects assumed they understood was not the foundation that actually exists on the other side of the moon. This is not a minor technical footnote. This is the kind of discovery that forces a complete restart of engineering assumptions for every agency that has been planning a far side installation. And the far side is precisely where the most strategically valuable real estate on the moon is located. The South Pole Aitken Basin, the same ancient impact scar where Chang'e 6 landed, has been designated as a target for NASA's Artemis missions. 9 potential landing sites have been identified, several lying directly within the basin, including Noble Rim 1, Noble Rim 2, and Hayworth. The reason these sites were chosen is not poetic. It is entirely strategic. The basin's permanently shadowed craters are cold enough, 3 times colder than the frostiest recorded day in Antarctica, to have preserved water ice over billions of years. Water ice that can be converted into drinking water for astronauts. Water ice that can be split into hydrogen and oxygen and converted into rocket fuel. Water ice that, if harvested at scale, transforms the moon from a destination into a refueling depot for the entire inner solar system. Whoever controls those water reserves controls the economics of deep space exploration for the next century. This is not chaos. This is strategy. And multiple civilizations are racing toward the same square mile of lunar terrain simultaneously. But what the AI analysis revealed about the basin's actual formation deepened the geopolitical stakes in ways that nobody had publicly articulated before. For decades, scientists believed the South Pole Aitken Basin formed from a massive asteroid striking from the south at a low angle. The directional assumption shaped everything, where debris was assumed to have landed, where mantle material was expected to be buried, and where future excavation might access the moon's deep interior. Then, in 2025, researchers led by Jeffrey Andrews Hanna at the University of Arizona analyzed the basin's teardrop-shaped structure with fresh eyes and discovered something that overturned the entire model. The crater actually narrows toward the south, not the north, which means the impactor came from the opposite direction than every textbook had assumed. It traveled from north to south, not south to north. This matters in a way that echoes far beyond academic journals, because giant impacts do not distribute their ejecta evenly. Material excavated from the deep lunar interior piles up on the downrange side of the collision, the direction the asteroid was traveling, which means the concentrated deposits of deep mantle rock, ancient radioactive. Material and geologically unique minerals are not where scientists had been mapping them for the past several decades. They are somewhere else, somewhere that now needs to be remapped entirely. And the AI systems doing that remapping are working at a speed and resolution that no human team could match. According to informed sources tracking this research, the implications for future mission planning are already triggering urgent recalculations at space agencies on multiple continents. NASA's Artemis Ivor mission, now targeting a late 2027 window for its first crewed lunar landing, will put astronauts down within the South Pole Aitken Basin into terrain that now has a completely revised geological understanding beneath its surface. China's Chang'e 7 and Chang'e 8 probes are in active preparation, targeting the same region as part of an international lunar research station that Beijing has been constructing in partnership with Russia and several other nations. And then there is the third player, the one that doesn't fit neatly into any traditional space agency framework. Elon Musk, standing at the intersection of SpaceX and the newly restructured SpaceX AI division, laid out a vision in February 2026 that most coverage treated as eccentric speculation. During an all-hands meeting following the $1 $25 trillion merger between SpaceX and xAI, Musk described a project called Moonbase Alpha. Not a scientific outpost, not a research station, but a supercomputing facility built on the lunar surface, paired with a massive mass driver catapult system capable of launching AI, manufactured satellites directly from the moon into Earth orbit. The computing power available from a lunar-based facility, Musk argued, would give SpaceX AI access to processing capabilities that no Earth-based competitor could replicate or even approach. The moon's low gravity and vacuum environment eliminate atmospheric drag. The launch economics become radically different, and the distance from Earth's increasingly crowded regulatory environment becomes, in this calculation, an asset rather than a liability. Most analysts wrote it off. A few took it seriously. But here is what almost nobody connected. Grok's AI architecture, at the time of that announcement, had already been processing the most detailed dataset ever collected from the far side of the moon. The same far side where Musk was describing a supercomputing base. The same terrain where AI analysis was simultaneously revealing that the soil was stronger, more structurally sound, and more suitable for construction than near-side alternatives. The same basin where water ice reserves make long-term human and machine habitation not just possible, but potentially self-sustaining. What most people are not seeing is that the scientific revelations and the commercial ambitions are not separate stories. They are the same story, unfolding on 2 tracks simultaneously, converging toward the same point on the lunar surface, and the moon's geological secrets are not finished revealing themselves. The Chang'e 6 samples unlock something else, something that the Chinese Academy of Sciences announced in July 2025, and that the international scientific community has been quietly processing ever since. The far side's mantle is colder, significantly colder than the near side. Analysis of the basalt samples, led by researchers from University College London and Peking University, and published in Nature Geoscience, determined that the interior of the lunar far side has been running at a lower temperature than the near side for billions of years.